Вот так на голову, а можно просто зацепить. Главное, чтобы вот микрофончик был там где-нибудь. Только
Ну, вы говорите.
So our today's speaker is Boris Doubrov from Minsk, and he will tell us about Cartan C classes of differential equations. Yes?
Yes.
Okay, you're welcome.
Thank you very much. Just a second, I'll adjust the microphone. I'll do it. One, two, three. Is it all fine?
Все в порядке.
Ага, отлично. Okay, so so indeed, I will speak today about Cartan's C-class equations. And this is actually old topic coming from the original work of Elie Cartan from 1938. And the title of this work is I'll just give reference with Contrandu 1938, pages 1689 to 1693. And the title is, in French it would be Les espaces généralisés et l'intégration de certaines classes d'équations différentielles. So, as I understand this, so it's just generalized spaces and integration of certain classes of differential equations. And you see this is a very short note, so it's just 4 pages. And actually, the only thing Cartan did on this note, it's not a complete article. He gave some definitions and examples and stopped there. So I'll shortly repeat his definition of what he calls a C-class differential equation and his main example. And Cartan treats this example in just 1 page, probably. We'll do this slowly, more accurately, to make sure we fully understand what's encoded in this very short note of Elie Cartan. So the definition. So a class of differential equations. Well, Cartan speaks about ODEs, but we generally may speak about, any differential equations. Is said to be C-class. That's exactly the term used by Elie Cartan. So at that moment, C doesn't come from Cartan, probably. So it's just C-class. That's his invention. If there exists a certain I'll translate some words into modern language. Lie transformation group. It's denoted like that. Well, typically this is an infinite dimensional Lie group, but may well be finite dimensional. So first of all, of course, it preserves a given class. So we want this group to act on this class of equations. And second, differential invariance of equations in this class with respect to G. So, we'll decode this word very soon. Are first integrals of the equation. So it's an interplay between many terms here. So first of all, we have to deal with, so this is just as it is. It's given in one paragraph, nothing else.
And what in case of PDEs?
Yeah, in case of PDEs, of course.
What are first integrals? Usually,
Yeah, you would need to go probably to infinite jets to define first integrals. But indeed, let's probably just, for the sake of simplicity, start with ODEs, and then I will discuss how, and this is actually the question I don't know the answer. I don't know the answer, what is the best generalization of this idea and techniques to PDEs. But there are some interesting examples that I've seen in action. So we'll start with ODEs for now. And
our first, to be more exact, are all differential invariants are first integrals, or all first integrals and only them?
No. So it's just one way.
Just
Differential invariants should be first integrals. Because, well, so let's decode now what it is. So a typical example would be, well, and he gives an example, probably by showing how this definition works. An example would make us understand better what he means by differential invariance of equations in a certain class, because that seems to be not clear what it is. And he gives an example. So he says, let's look at a very basic example where we deal with first or second order ODEs, scalar second order ODEs. And our group will be just diffeomorphisms of the plane. So this is what's normally called point transformations. And of course, this group acts on equations. So to be precise, not exactly this group, but well, to have like to move to modern language, we have to think about second order ODE as a hypersurface inside second jet. Well, let's assume we deal with maps from R to R, although we can speak about also jets of submanifolds, but for simplicity, it's just a codimension one. So a hypersurface in second jets. Then, of course, our group prolonged 2 times acts on this space and induces the action on equations. And at that point, we can start thinking, so acts on E, on equations of second order. And at that point, we can start thinking about differential invariance, because now we are in the situation where we have a class of submanifolds, like just any hypersurface sitting in this, that would be a 4-dimensional manifold. Then we have a group. And whenever we have a transformation, Lie transformation group acting on any manifold, we may start calculating differential invariance of submanifolds on this manifold. This is a general theory set up by Sophus Lie, I think back in 1884. But in practice, this means that what we do next, we now look at jets of such submanifolds, jets of equations, so to say. We now look at how our group prolonged to jets of equations acts, and what would be the functions which are invariant under this action. And these functions will be exactly differential invariants of equations. So the transformation group is huge. So it's transformation, it's all point transformations. So if you were to think, if you were dealing with like invariance of curves in R2 with respect to such action, we wouldn't have any, because any 2 curves, at least non-singular curves, would be current locally under the action of the group of diffeomorphisms. But since we are now lifting this group to second jets, so it's not that big, it's not all transformations of this four-dimensional manifold. It's those particular transformations that are like lifted from R2. And then hypersurfaces, which are our equations, will now have non-trivial invariance. Again, this is a very classical theory. One needs to go to, and this theory is due to Tres originally. So Tres and probably around 1884, something like that, if I'm not mistaken. Oh, maybe later. No, it's 96. So 84 is the original paper, obviously. So what Tess did, he exactly implemented this approach. So he now started acting on jets of equations. So to be precise, we have to now act on jets of any order because we want to think about any just invariance, differential invariance of any order. Then we would have to act on, I think this is a notation. So these are jets of three-dimensional submanifolds in this manifold. So essentially, these are jets of equations. And the group we would be acting would be our diffeomorphisms prolonged 2 times so that they start acting on this manifold. And then we have to prolong them k more times to act on this space. And so it will act on this space, and the functions which are invariant under this action would be called differential invariance of order k. Differential invariance of order k of second order ODEs, to be precise. Now we, of course, when we speak about invariance, we also want to speak about relative invariance. So relative invariance would be not the functions which are invariant under the action, but functions which gain a non-zero multiplier under this action. So I will distinguish between relative and...
Sorry, may I ask a question?
Yeah, sure.
Боря.
Yeah.
Привет, Боря.
So,
but I can't understand where is your first integral comes from. Do you mean that for every second order equation you can construct a first integral? This is not possible, right?
No, so not yet. So I'm just explaining what does it mean, what is the differential invariant of an equation in general.
But I mean, this general class of second order equations cannot be C class.
No, not at all. We need all right, extra conditions to make
it. Okay, that's fine. Thank you. Yeah.
C class. No, not yet. We are just very slowly moving towards towards the answer for the second order ODEs. I just want to be very precise here so that we all understand what's going on. And well, so relative and absolute invariance, I think I don't need to speak about this in detail. So we know that absolute invariance is just functions which are invariant under this action. Relative invariance are those functions which gain a non-zero multiplier. So essentially only zero set of such functions is invariant. So I'm saying this because the very first invariance of this second order ODEs under point transformations appear only when k equals 4. So you need to go up to jets of order 4 to get very first relative invariance. And this relative invariance have very explicit forms. They've been computed. So Tess did all detailed computations here. And you get these 2 relative invariance. So one of them is just force partial derivative of function f with respect to y prime. So this is exactly a function on this space, which I write it like that. So it's like jet coordinate on this space. Is it all fine? Yeah. Oh, okay. I thought something is wrong with it. So again, I'd like to make sure you'll understand what's going on here. So what's written here is I identify our equation with a graph. Equation is a submanifold of dimension 3, but I identify it with a graph of a function f. Function f goes from R3 to R, essentially. And this is a jet coordinate on this space, on G, where k equals 4. So, and again, this is a relative invariant, very, very important. Relative. The second invariant is normally denoted by W, is very much more complicated, but I will try to fit it into the blackboard. Probably I'll have. So what I'll use some special notation for this. So to denote the derivative with respect to y prime, I put an index 1, so it will be like that, 4 times 1. This resembles more and more standard jet notation. So in case the other invariant is this one. This is probably the only formula which I will write in full, just because I want to. No, that's X here. Just to give you an example of what kind of formula we have to deal with. So, so f1 is a partial derivative with respect to y prime. F0 is just a partial derivative with respect to 0. X is a partial derivative with respect to the total. So it's a total derivative. So fx is df by dx plus y prime df by dy plus f itself, because it's restricted on the equation, df by dy prime. So these are the formulae and the very explicit formula for this second relative invariant. And then if you go, one goes to k equal to 5, 6, etc., one gets absolute invariance finally. And Tess did exact computation of the number of these invariants, constructed invariant differential operators that generate the algebra of invariance. So all this according to the standard definition side saves, obviously. So it's just a huge monstrous computation. And he did it without computer, of course, at that time. It's a paper of about 100+ pages, full of dense computations. Because one can imagine that you have to be very smart, prolonging such action, writing explicitly the action of such thing on jets of order k, where k is 4, 5, etc. So you can count the number of variables. It's like close to 100 of jet derivatives that show up here. Well, maybe less, at least dozens. So now, example for Cartan. He says that equations that satisfy this thing are a form C class. So this is an example, very first example given by Cartan. He says that second order ODEs satisfying equation W equal to 0 have this very special property that all other differential invariants we killed one, all other differential invariants will be actually first integrals. So, Zhenya, this is now the proper definition of this example. Is it all now fine?
Okay, thank you, Boris. Thank you. I see.
So let's try to understand how he could come up with such example as such monstrous computation. Certainly, there is some rich geometry behind this example.
And he knew the result by Tess.
Yes, of course, he knew the result. He actually, I think around 1920s, Cartan repeated the same computation, but in a much smarter way. using what we call today Cartan connections. And I will mention this as well today because this will be a very important technique for proving at least results similar to this one. So to actually prove such statement that any second order ODE, so all invariants in the class of second order ODEs satisfying this equation they have this property. I don't think it's doable by hand. Of course, it's a computational task. It probably can be reformulated in a purely computational manner and maybe on today done by computer, but of course, it's very much more interesting to understand what kind of geometry is behind this statement. So let's, okay, I'll clean this board because I think we all know now the definition. So first of all, let's look at this much easier relative differential invariant, because for this invariant, we have, well, as we discussed, this is just relative invariant, so only vanishing of this invariant makes sense. So it also has a very transparent meaning. So it also defines as a class of second order ODEs, but in this case, it's very easy to understand what these equations are because it's just equations which are cubic. So our function would be cubic, so 0 plus a1 y prime plus a2 y2 primes plus a3, oh, sorry, y prime squared, of course, plus a3 y prime cube. So this is like where ai's, of course, functions of x and y. So this is a class, another class of second order ODEs, but it's not of C class. Yet it's very well known in the geometry. So it's very well known that such class is preserved by any point transformations because, and that's also an easy computational exercise to just prolong any point transformation to second jet and check how it transforms these equations and see that cubic polynomial property, the property of this right-hand side being cubic is preserved. It is also very well known that such equations are in one-to-one correspondence. So in one-to-one correspondence with so-called projective connections on the plane. R2. So I don't want to spend a lot of time on what it is, what is a projective connection, how it is defined. The definition of projective connection is actually quite simple. Well, in any manifold. So projective connections are equivalence classes of affine connections, where two affine connections are called equivalent if their geodesics are the same modular reparametrization. So it can be also expressed in terms of connection form, etc. But like in the scope of what we need, it's a very simple definition. Essentially, projective connections are equivalence classes of affine connections which have the same geodesics viewed as unparameterized curves. So varying. Okay. So and actually, this equation is exactly the equation on geodesics of this projective connection. So this is how one-to-one correspondence is established. We want, so and again, that's kind of trivial computation. So you take an arbitrary affine connection. You, first of all, write classical equations on geodesics as parameterized curves. Then you exclude the parameter. So you use just where you view y as a function of x instead of x and y as functions of t. And then you see that you arrive at this equation. And these coefficients will be exactly the very explicit expressions of the coefficients of this affine connection. And you'll see that you arrive at the same equation if you don't leave two affine connections IQ. So what happens now? Actually, since we have this one-to-one correspondence, we now know that invariance of this object under the transformation group or under all diffeomorphisms we have is the same thing as invariance of this class of equations. So we may compute invariance in two ways. One of them is doing like this jet space-like prolongation and well, prolongation and then, well, classical Lie approach, let's put it like that. Another way is to look at projective connection as via connection form, and then start computing curvature, or doing the same thing as we would do in case of Riemannian connections, Levi-Civita connections. So we have a curvature, then we start differentiating it and getting using covariant derivative, and then getting more and more invariance. So one important thing is that both approaches give us the same answer.
I'm sorry, may I ask a question again?
Yeah, sure.
Boris, let's return to your example.
Yeah.
When W is 0, right?
Yeah.
W is 0. So the statement is every differential invariant is the first integral.
Yes.
So in this case, if we do not impose this extra condition, F1111 is 0,
yeah,
but just W is 0. So can you write down any differential invariant explicitly to see that it is a first integral?
Yeah, so again, all differential invariants are written down explicitly in the work of Terrace. So I refer to this paper where you have like the complete description of all invariants, not just those which satisfy for arbitrary second order ODEs. And of course, inside this computation, you'll see this invariant showing up. So if you assume that W is 0, part of the invariance will vanish, but part will survive. And as they're written down very explicitly, it is very easy to see which of them survive. And unfortunately, I'm not able, so I'm not prepared to just write down explicitly the formulae from this paper. But I just guarantee you that they're very explicit, very precise.
Okay, thank you.
So it's really not that I'm. So it's a very constructive technique to write all invariants.
But this relative invariant, it doesn't give first integral.
No, because it's relative.
Relative. Okay,
So
okay, thank you.
You need to have to go to fifth jet to get first absolute invariance. But in general, so the complete description of the algebra of differential invariance here is like that. So you have a few low order invariants, let's put it like that, and operators that generate the rest. And all of them are given very explicitly in coordinates, in jet coordinates of this space, of course. So it's very constructive technique. But this is exactly what I'm saying. To check that this condition implies that all other invariants are first integrals, I don't know how it's doable without the geometry. It's probably doable as an explicit computation because, well, you may express everything in coordinates, but equations really become monsters. Maybe there is a smart way to do this. But, well, I just follow the Cartan's approach where he proposes the proof that is based on this kind of interplay between invariance of equations and invariance of certain geometric structures, which in this case are projective connections. Actually, what's going on here, we are doing very interesting trick here. So this thing can still be viewed as a certain submanifold in second order jet space. Yes, it's cubic with respect to y prime cube, but it's still a submanifold in this space. So what we are doing, looking, instead of checking the invariance of submanifolds, we start looking at invariance of geometric structures. So geometric structures are intrinsic objects. This is what I'm saying. We normally call this as extrinsic approach and intrinsic approach. So extrinsic approach means we take extrinsic and intrinsic approach in computing differential invariance. So let's be more limited to what we are doing. So extrinsic approach means we view them as submanifolds. We look at jets of the submanifolds, prolong our transformation group to a certain level, and look for invariant functions.
Boris, sorry, one more question. Am I right that now you are narrowing your C class? You are adding to W equals 0. You are adding this extra condition.
No, I'm trying to prove why this happens. And I'm starting by looking at a different class, which is not C class. So I'm looking at a different class of equations. Now, I'm looking at the class of equations which satisfy not the equation W equal to 0, but the equation I equal to 0. Okay. Because it's easier to understand for us. And I'm just showing that how we can use the ideas from, well, Elie Cartan and differential geometry in general to get differential invariance of equations. So it's actually a very important thing that's going on here. So instead of computing differential invariance of equations, we switch on two connections. And for connections, we use techniques, as I say, equivalent or analogous to techniques of coming from Riemannian geometry, like curvature tensor and covariant derivatives, to get the invariance. These are kind of different classes of invariance because these invariants, like extrinsic invariants, live on jet spaces of submanifolds. Intrinsic invariants are certain expressions of the curvature tensor and its derivatives. But because the curvature tensor itself is expressed via these coefficients, in the end we get the same result. But this was about this class of equations. We are not interested in this one. Instead, we are interested in the other one. And by the way, if you ask what happens if both of them vanish, then it's well known that the equation is trivializable. So this is a condition also well known, actually back to Sophus-Lee probably, that second order ODE is trivializable, meaning it can be brought to a trivial equation by certain point transformations if and only if both of them vanish.
What do you mean by trivial equation?
Trivial is, of course, just y2 prime equal to 0. This is for me trivial equation. Well, yeah, that's a good point, but simplest possible, I don't know. But no, I call this normally trivial and then call another equation trivializable if by change of variable we can bring it to a trivial one, but it's just a terminological thing. So now we look at this ones. So what is this class? What is the geometric meaning of this class? The geometric meaning of this class is actually dual to this ones. There is a notion of duality in class of second order ODEs. That's very special for second order ODEs. In general, it's more complicated. But for second order ODEs, if you look for general solution, it would depend on two constants of integration. Let's say A and B. And if we would want to have a general solution, we can write it as a certain function g of x, y, a, b equal to 0. So it's a general solution of our of this equation. Of course, to find g, we need to integrate the equation officially. But let's assume we did this. So we got a general solution written in this form, and then duality means we just interchange, like in projective duality, we swap x and y and a and b. Now we look at a and b as our independent variables and x and y as constants of integration. Then we would get a two-parameter family of curves on AB plane. And of course, it's solution space of some second order ODE. But now, like we can view B as a function of A, for example. So we get dual ODE on B of A. Well, of course, it's just a parameterization. We assume that curves can be parameterized, for example, by A. So what happens is the statement is like that. So this dual equation is cubic if and only if the initial equation satisfies this condition, W equal to 0. So these two invariants actually are dual to each other, and in the right coordinates, they are like equal in a way. It's just a poor choice of coordinates or classical choice of coordinates that makes one of them very simple and another very complicated. But geometrically, they're actually equivalent. And of course, in case of, it's actually very transparent if you look at the equation y2 prime is equal to 0, then we see, like, if you take y2 prime equal to 0, then y would be ax plus b, and then immediately we see that b is a linear function of a if you now treat x and y as parameters, so we get the equation b2 prime is equal to 0. But well, to be precise, what like that, just not to confuse what we use, which variable we use as an independent variable. But that's just really a trivial example. In general, this duality works for any nonlinear second order ODEs, and it establishes duality between these two invariants. So now we understand what does it mean W equal to 0. We have a proper understanding of this C class. It's just those equations whose dual equations are cubic with respect to, well, the first derivative.
Well, just to,
Yeah.
how can it be proved?
How it can be put?
Proved.
Approved.
Yeah.
Well, there are multiple ways.
Just an idea.
No. Well, you can even complete this explicitly. Yeah, these expressions are not that huge, so it's doable by explicit computation. And again, I think there are multiple places where it's done, including, I think, also a classical book of Arnold on geometry for these. He had the chapter on the geometry of second order ODE, so I think he should have mentioned this idea as well. So again, what I'm trying to do now is just explain why equations second order ODE satisfying W equal to 0, condition W equal to 0, are indeed of C class in terms of Elie Cartan. So what will happen now? So let's see. So we now reached the point where we kind of proved that this class of equations described by this condition W equal to 0 is exactly the class of equations whose duals are cubic with respect to the first derivative. But now, if they are cubic with respect to the first derivative, so essentially they have the form to be a Z1 B prime plus Z2 B prime squared plus Z3 B prime cubed, where now Zi's are actually functions of A and B. So this is what this condition means. And again, the way to go from here to here is actually impossible. So you need to solve the equation to write this to write this system explicitly. It's just theoretical reasoning, not practical. But now we know that such thing happens to be in one-to-one correspondence with projective connections. But now projective connections will be not on the original XY space, but they will be on AB space. Well, I call this AB space like parameter space, solution space, actually. So this will be projective connection on the solution space. Now this projective connection will have invariance. All these invariants will produce as functions just in A and B. They will not depend on anything else. And we've kind of proved already that this invariants are in one-to-one correspondence with this invariance. So therefore, and we get that all differential invariants, so the reasoning like that, all differential invariants of this equation satisfying these conditions can be expressed as invariance of the projective connection on A-B space, and therefore they will only depend on A and B. Therefore, they will be constant on solutions. So that's naive reasoning, and I can make it more precise if you can, if needed. Actually, I'm just trying to understand the basic logic behind this theorem or Cartan example. And again, everything was written on just one page in Elie Cartan's paper. So what I was trying to explain now is one page of a text about of that reasoning. So what does it mean now in practice? So theoretically, we know. So theoretically, we can prove, or we've proven, according to Cartan, that all differential invariants of equations satisfying this condition will be expressed only in terms of the parameters of integration A and B, and therefore they will be constant on solutions. Because for each solution, of course, A and B are constant. So what does it mean? So suppose we want this to turn into machinery and algorithm.
But is it obvious that when we pass to GDEq equation, differential invariants pass to potential?
That's a very good question. So actually, invariants of this second order ODE are nothing but invariants of this surface viewed under transformations that transform X and Y and A and B independently. They do not mix X and Y and A and B. And this actually can be used to prove that differential invariants of this equation are the same thing as differential invariants of these surfaces. So this will be surfaces in R4, but viewed under a different transformation group.
Of course.
Yeah, under a transformation group, which is a direct product of two groups of diffeomorphisms of R2. One transforming A, X, and Y, and another transforming A and B. And then, using this equivalence, we now know that differential invariants of the original equation are the same as differential invariants of the dual equation. Because this thing is, you can easily swap X and Y and A and B.
But here you consider the diffeomorphism of A and B.
So I kill X and Y, I exclude them when I write this equation. So it goes like that. So I start with this equation. I reformulate this equation. Equivalently, I write this equation via the solution. So I solve this equation. So I turn this equation into a two-parameter family of curves on R2, essentially. So when I write the thing, I just have a two-parameter family of curves in R2. But if I have a two-parameter family in XY, I also have a two-parameter family in AB. And I exclude the X and Y and get a dual equation. It's all it's all well defined. All the passages are well defined, and shows that differential invariants of the original equation are the same thing as differential invariants of this relation, and therefore are the same thing as differential invariants of the dual equation.
But this is specific
of second order ODEs. Yes, that's a very special thing about second order ODEs. So suppose, so at that moment, we would like to understand, does it make, so is it really tautological theory, or does it have any practical applications, at least theoretically? So as Jenny, you were asking at the beginning, can we explicitly write down any other invariants? Yes, we can. So we can check that our equation belongs to this class. Yes, we can. So if you have any equation, so this is a kind of an algorithm. And I'm saying kind of because nobody was able so far to implement this, unfortunately. And I don't know whether it's really computational complexity is just a lack of applications. But the algorithm would work like this. We have an arbitrary second order ODE. We check if it satisfies this condition, if W is equal to 0. If yes, and we are in this C class, then we can find some first integrals by just applying Tress formulae, computing other differential invariants, in getting some functions, which will be, according to Lie-Cartan theory, first integrals of our equation. So it sounds a bit strange, but if our equation of C class, then we're able to find first integrals without integration at all. So it's like, sometimes it's called finding integrals by differentiation, because the only thing needed to compute the values of differential invariants is to differentiate. We do not need, and we have explicit formulae for them, thanks to Tress. So this is actually kind of funny consequence of this story. So whenever we can even go through Comke list of second order ODEs and check how many of them belong to this class and how many of them could have been probably solved by just differentiation.
Bora,
Yeah.
but if you take the easiest of non-zero Tress's invariants,
Yeah.
how horrible is the expression in terms of the function f?
Yeah, I did this in Maple up to order 6 or 7, and the
easiest of them. What's the easiest?
Yeah, they will fit into one page on computer.
Just the easiest requires one page. Yeah. All right. Okay.
But of course, explicitly, because well,
right.
you might not need to write them. You may optimize computation because, of course, when Tress writes formulae, it's not just one single huge polynomial. He computes some intermediate terms and then expresses the final invariance in these terms. So you may even probably shorten the definitions of invariance into a few lines, but I have to be careful here. But again, they're just differentiate. They're all algebraic. So all these differential invariants are algebraic in function f and its partial derivatives. So it's like computing a few partial derivatives and then computing a polynomial, say, which has 20 or 30 terms. So I don't think this is a terribly difficult computationally. Okay, so that was an introductory part of my talk, actually. And I will try now to move forward and generalize this to arbitrary systems of ODEs, meaning not just scalar ODEs, but systems of ODEs, and the order will be arbitrary as well. Well, arbitrarily high. So I will skip order 1 because for order 1 we know that we don't have invariants, non-trivial invariants. So any other questions at that moment before I start moving forward? Because I think it's been a very important reasoning here that we start playing between extrinsic invariants of submanifolds and intrinsic invariance. So like looking at differential structures on the equations and forming some kind of connections to compute the invariance. Okay. So I will probably, yeah, I will need that. So now we would be considering an arbitrary, and for just computational reasons, more convenient for me to have n+1 here instead of n. Right now, y is a vector of m variables. So it's actually a system. What's written here is a system of m equations of order n+1. And we'd want to find out other classes, C classes. And I'm saying that I'm trying to find some other classes of equations that satisfy C class condition of Cartan. And these are in no way unique ones. We have always trivial classes. We may have a class of equations which all equivalent to a trivial one, which means they have all invariance vanishing. That will be a well-defined C class because all invariants vanish. They're all constants. But it's kind of a trivial example. What I will show is a non-trivial example. And the assumptions will be like this. So our group under which we will look for differential invariance will be either point transformations. So it will be diffeomorphisms of R m+1, or to be precise, just no, probably R m+1 is good. If m is greater or equal to 2, so it's point transformations if you have a system of at least 2 equations. And if m is equal to 1 and n is at least 2, meaning we speak about at least third order scalar ODEs, we already treated second order ODEs. So it's third order ODEs or higher, we'll speak about contact transformations. So I don't know what would be the best way to denote the contact transformation. So it will be R3, with first jets preserving Cartan bundle. Let's put it like that. So these are point transformations, they're contact. And there is, of course, the logic behind the choice of these subgroups. We can choose pseudogroups, sorry. We can choose different pseudogroups here, like fiber preserving, etc. But these are like the biggest ones, preserving the notion of a finite jet. So not increasing the order of ODEs if we apply these transformations. In fact, we are able to find out, and that's this was a program that probably so historically the case, the scalar case, so it's m equal to 1 and n equal to 2, and 1 and 2 were done by Cartan. So it's second and third, so second and third order ODEs. Then n equal to 3 was done by Bryant, I think around 1989. And around this time, m is greater than 1 and n equal to 1. So it's systems of second order ODEs were done by Mark Fels, I think. Fels also around these dates, but I'm not sure. Probably like that.
And Brian dealt with scalar.
Yes, scalar force order ODEs, but as usual for him, it was just side effect of the developed theory. He was looking for special holonomy. And for him, the best way to construct special holonomy was to come up with to prove that certain class of fourth order ODEs is of C class actually, and then using this, he proved that the existence of irreducible GL2 is a holonomy. Reducible G2 sitting in irreducible four-dimensional representation is a holonomy of torsion-free affine connections. So it's like, it's a more complicated story than just treating C-class equations. And for files, of course, it was also not just C-class equations, it was constructing connection for arbitrary second order systems of second order. And as a side effect, he identified which part of the curvature in this connection is responsible for the equations being C-class. I think in around 2008, it's me and I think Maciej Dunajski more or less independently, well, probably 8, found out how this generalizes to any scalar ODEs, and then to systems followed more or less immediately. So it's Dunajski. Yeah.
To understand, Bryant and Fels.
Yeah.
What did they do? They presented some examples of C classes or gave a complete description?
No, well, there is no complete description of C classes, as I said, because what I'm trying to show is more or less generic C classes.
No,
Yeah. So in both these cases, in all the both two cases, essential technical part of this work, both for Bryant and for Mark Fels, was to establish this correspondence we've seen already for cubic second order ODEs. So establish the correspondence between differential invariance via extrinsic approach and certain connections. So in both cases, they were constructing connections canonically associated with classes of differential equations. And as soon as they had connections, they were able to prove that all differential invariants of equations come from these connections, and then it was not that difficult to identify which part of the connection vanishes along each solution. So it was a technique, and actually the same technique was used by me to prove the general theory. So I was also constructing connections associated with differential with systems of ODEs. So now the result, and the result is surprisingly easy to describe. I already mentioned what is a trivializable. And again, if you have a better word for this, I'm fine. So trivializable always means equivalent to something that is like that. Under certain groups of transformations, we always have to specify what would be our pseudo group, which we use to trivialize certain equations. So I would also need this notion of trivializability for linear equations. So if I now look at an arbitrary linear differential equation, so now I write it like that. A linear homogeneous. And again, y can be in Rm. So it's an arbitrary linear homogeneous equation. And I can also think about what would be the differential invariance of such equations, but I have to reduce my pseudo group. Because of course, the property of equation being linear will not be preserved under arbitrary transformations. Whenever we have a linear equation, we have a certain vector bundle actually. So we would need to preserve the structure vector bundle. So the transformations that would be allowed would be these ones. So this is the most general transformation that preserves classes of linear equations if at least n is 1. So for first order, it's a bit different, but starting from second order, this is the biggest transformation, group pseudo, well, Lie transformation group or Lie pseudo groups that we can take as equivalence group for such equations. And I, of course, I mentioned explicitly that I deal with equations, not just with operators. But well, that's almost one-to-one because I assume the leading coefficient is one. So whenever I have the operator, I can write the equation, and vice versa whenever with the leading coefficient one. And here lambda is just diffeomorphism on X on the line, local diffeomorphism. And mu is an arbitrary, of course, mu of X would be in GLM. Well, depending on X, of course. So these are the transformations. And this is, again, yet another classical problem. And I just mentioned that the complete system of invariants for such linear differential equations was written down, again, very explicitly by Wilczynski in 1905. Again, very, very classical theory. So he came up with expressions which I denote today W3, W4, etc. Well, actually W2 as well. Wn plus 1. They will be valued in endomorphisms of Rm. So actually matrices M by M matrices. They are explicitly written down as polynomials of these coefficients, which are also matrices, and their derivatives. And they form, again, the complete system of relative invariants. Complete system meaning all other invariants, including absolute ones, can be obtained by using invariant differential operators. And our equation will be trivializable. I use the same word here. Trivializable if and only under these transformations, if and only if all these invariants vanish identically. And so these are actually arbitrary matrices with one exception. So trace of W2 should be 0. So therefore, in scalar case, this kills W2. In system cases, it just kills the trace of W2. For other invariants, it is not applicable. And again, actually, the construction of this invariance is can be done very explicitly. It's about 5-10 pages of explicit computations. And the idea is very simple. So you use this freedom to kill what you may kill. For example, you notice that by careful choice of mu, you can kill the leading coefficient after the highest derivative. So you can choose mu of X such that Pn becomes 0. Then you may try to choose lambda such that you are not able to kill Pn minus 1 because Pn minus 1 is M by M matrix and lambda is just single function. But you can kill trace of Pn minus 1. So you essentially you can always achieve Pn equal to 0 and trace of Pn minus 1 equal to 0 by a careful choice of lambda of X and mu of X. And this is well known as a Laguerre-Forsyth canonical form of linear differential equations. And then only a finite dimensional transformation group will be left. We are not able to kill completely lambda and mu. We're just able to kill them up to a finite dimensional transformation group that would preserve this Laguerre-Forsyth normal form. But then computing invariance is essentially linear algebra representation theory of a finite dimensional transformation group. More precisely, it's just a cell tool showing up. So some freedom is here, like fractional transformation, linear fractional transformations of X will remain, and the trick will be to kill them, or to find out what is invariant under such transformations. And so again, this is another topic. I don't want to dwell into details here. I'm just saying that this is a well-established theory that comes with very well understood invariants. So what happens next? So next is to turn invariance of linear equations into invariance of nonlinear equations. And of course, well, today it's well, so it came for me as a big surprise when I found out how it works. But now I really realize it's trivial. So you just have to use linearization. Or to be precise, you turn the equation, you write down the operator of universal linearization for this equation, and just compute these expressions for this operator, where now derivatives will be replaced by total derivative. And that's it. So what will happen? The same expressions can be, so W2, W3, etc., Wn plus 1, generalize to become, well, they will be relative invariance of this system, of this system, generalize in such way, such that restricted to each solution, they reproduce or calculate classical Wilczynski invariance for the linearization. Along, so restricted to each solution y of x, y0 of x, if you like. Along y0 of x. But essentially, the idea is to go to the, well, as I said, so you go to the operator of the universal linearization and just formally compute the same expressions given here, because we use the fact that these expressions are polynomials in terms of the coefficients and derivative with respect to x, and just ordinary derivatives. So therefore, it is, again, we use the fact that the operator of universal linearization behaves under these classes of transformations exactly in the same way as this equation is transformed under this transformation. That's, in a way, is the sense of this universal operator of universal linearization. So, the meaning of vanishing of this invariance here, when they become invariance of nonlinear equations, changes a little bit. So here, this invariance were vanishing identically if and only if our equation was trivializable. In nonlinear case, they vanish identically if and only if the linearization along each solution is trivializable. So it's a different condition. So linearization essentially describes us a tangent space to the solution space. So if you fix a solution, it will be a point in the solution space. Then the linearization will describe us variation, meaning we describe the tangent space to the solution space at this solution. And so we get a trivial linear equation at each tangent space of the solution space, instead of just globally trivializable system. And you may ask, what happens? Is it known that there are some other invariants? Is it known that if such invariants vanish, we still get some non-empty class of equations? Yes, we can prove this, and I'll come to this. And actually, this is thanks to the results of Boris Koblikov and Jennifer Ponte, we know how generic are classes of such equations. So now the main theorem. So the main theorem today is condition W2 equal to W3, etc. Wn plus 1 equal to 0 defines C class.
You mean these generalized W?
Yes. So yes, I would probably normally I denote them by a curved W, probably just like that. So yes, this curved ones. And this is consistent exactly with the results of Bryant and Fels. So the conditions they found, they just didn't know that these are just these ones. And they didn't know the meaning of them. They just computed some connections, some part of the curvature. So I think it was thanks to Maciek Dunajski who hinted first what would be the real meaning of the thing. So I formulated the statement. The statement is surprisingly simple. So the conditions that all linearizations are trivializable defines as C class. The proof is, well, it took like 5+ years to prove this. And the proofs appeared, so proof appeared in the paper of me, Dennis, there, and Andreas Chap. In archive, it is somewhere around 2017, but of course, it took some time to get it published. I think it was published in 2019, finally. So before going into some techniques of the proofs, so the ideas of the proofs are kind of similar. So we also construct Cartan connection. We also identify these conditions as a part of the curvature that vanishes. But then we have to work hard and use very, well, non-trivial techniques in the Lie algebra cohomology, but finite dimensional Lie algebra cohomology, so nothing really terribly complicated, to prove that this condition is sufficient. But it really boils down to some algebraic computations around cohomology of finite dimensional Lie algebra. And this finite dimensional Lie algebra is exactly the symmetry algebra of the trivial equation. Again, not surprising. So, but But I'd like to speak a little bit more about these conditions and in general the principle applied here. So,
Borja, question.
Yeah, sure.
Can I understand this result as follows? So I take this your system's star,
Yeah.
okay? And I take, say, point transformations. I construct all possible differential invariants I can, right?
Yes.
Then I require that each differential invariant is a first integral, right? So I just differentiate this first integral and use the equations, right? And then this gives me exactly, if I do this for all invariants, I get precisely your curly W's equal 0, what I get as a result. So I don't need to invent them. I just get them from invariants.
Well, we did it other way around. So we first, assuming that we have them zeros, we prove that all other invariants are first integrals.
No, but it's exactly, I think I can reverse it. So I don't need to guess them. I can just get them from invariants. You have invariants, you differentiate them, use your equation star, and this gives you equations for the right-hand sides precisely. Am I right? So you get your W's more or less for free. You don't need to invent them.
Yes, I think this is how Dunajski and Todd constructed them for scalar E's.
Okay, okay. Thank you.
So
thank you.
they were doing exactly this thing, but that worked for scalar E's, and they also didn't initially understand what's the meaning of these expressions.
So maybe for second order equations, let's return to your first example, scalar second order equations. Right? So suppose I don't know this W. Suppose I don't know. I just take these stress as invariants. I differentiate them and use the right-hand side substitute F for Y double prime if it appears, right? And then this will give me a system of differential equations for the right-hand side F.
And this would be exactly the equation W equal to 0.
And it's a miracle that all of them are equivalent to just one condition, W equals 0. Is it correct? It's a miracle in some sense. Right?
Yeah, well, it's a miracle as a result. So this W certainly shows up in all the stress invariants in a very natural way.
So you probably take the easiest stress invariant. You differentiate it, you get W equals 0. But then
you prove that.
But if you take other stress invariants, it's a miracle that they give you exactly the same. Right?
Well, I thought I tried to explain you.
No, I understand. But okay, thank you. That's fine.
But yes, if you just do this, if you would want to forget about differential geometry at all and use just jet calculus, then probably this is what you would end up.
All right.
A few very important things. What happens here, we impose conditions in our equation by imposing certain easier conditions on the linearization of this equation. Because, of course, linear equations are much easier to handle and understand. And in particular, in this case, we impose the conditions that linearization is trivial. Or trivializable, sorry, so it's just to be precise, trivializable. And to my knowledge, this condition did show up quite some number of times in other works already. And Jenny, if I'm correct, you also have a statement for dispersionless, second order dispersionless equations that if a linearization along each solution is like a trivial conformal structure, then the equation itself is trivializable.
Yeah, more or less. Yeah.
So then there are also important. So in works of Zhenya Feropontev and Boris Kruglikov and others, we have reformulation of integrability properties of dispersionless equations via the properties on the linearization. And again, it's a bit more complicated than just requiring them to be trivializable, but it's like semi-trivializable, I would say, semi-flat. So some part of the invariance of linearization has to vanish, and this guarantees that the much more complicated equations will be integrable in terms of hydrodynamic reduction principle or techniques. Then, so certainly such conditions and such logic does appear not only in case of ODEs. So it is very important. I think it's kind of a today for me this became at least one of the primary techniques for studying any equations at all. So you first look at the linearizations and look at what you can impose, what kind of conditions you get on the linearizations. Sometimes, assuming that your linearization is trivializable is too strong. It just kills all freedom, all interesting equations. Sometimes the conditions that show up are milder than just these ones. So that's one thing I wanted to mention. Second is how generic is class of equations that satisfies these conditions. Because these are, well, these are quite huge expressions. It's not immediately transparent whether they're consistent at all and how to understand how many equations satisfying these conditions one has. And I cite here yet another work by Evgeny Ferapontov and Boris Doubrov, that in the scalar case, at least for m is equal to 1 and n greater or equal to, I believe, 2, so at least third order these. This condition, then W2 is equal to 0 automatically in this case. So we have to start with W3, W4, etc. Wn plus 1 equal to 0. So these conditions themselves, and if we may treat them as a system of PDEs on the right-hand side. So this system is integrable in the sense of hydrodynamic reduction. Yeah. Because it's you have too many variables here of hydrodynamic reductions. And the freedom you get finally, I think, is 2n minus 2 because I switched. So I think, Jenny, in your original work, you use n instead of n plus 1. 2n minus 2 functions of 3 variables. So this is the freedom you get. This is how many equations in the C class you get. And here another mystery. I've never seen any such equation explicitly. I've seen them. No, just to be precise, I've seen some examples of equations satisfying this principle, satisfying these conditions. Sorry. But they've all constructed artificially from known solutions. So one first constructs solutions and then writes the equation. And the main idea is to use some complex, global complex geometry, in fact, and Cadere theory, deformation theory of rational curves. So the basic technical tool of constructing examples of such equations is as follows. So one takes a complex Z2 and a rational and just a rational curves inside Z2. A single rational curve is sufficient. And then so complete deformation family would depends on n parameters, n plus 1 actually parameter. And complete deformation family is just all rational curves. In global complex geometry, when you deform a rational curve, it has to stay rational. So it will be some finite dimensional family of. Yeah, I'll tell where n comes from. Where n is actually the normal bundle. So let's d by Tn is of type O. So it's a one-dimensional vector bundle over a rational curve, and all bundles, vector bundles, line bundles over rational curves are well classified. So it has to be of type O. And then you get n plus 1 parameter family. So it all depends on what kind of normal bundle this rational curve will have. For example, if you take a line inside P2, it will be O1, and there will be a two-dimensional deformation family, and will be all lines on P2. So from starting from a line in P2, you get a equation y2 prime equal to 0. But one may take, for example, a conic in P2. That's also a rational one. And then as a complete deformation family, one gets all conics in P2. All conics in P2 is a 5-parameter family. So it's O4 will be, for conics, it will be O4. So it's 5-parameter family. And the equation will be the equation that defines all conics. It's well known fifth order ODE, and I can write it explicitly. Just thinking if I can write it. Yeah, I have a formula for it. Just to be sure I'm not confusing the coefficients. Just a second. Yeah, so it will be the equation like that. 9y2 prime squared y5 primes minus 45 y2 primes y3 primes y4 primes plus 40 y3 primes cube equal to 0. So this is the kind of equations you get. This is the equation exactly in the C class. So it will have this generalized Wilczynski invariants, as they call them, vanishing. But you get it not because you solve the system. You get it because you use this trick coming from complex geometry, and this trick is due to Bryant, actually. Or Hitchin maybe first. Hitchin. Well, I put Bryant because I learned it exactly from his paper on fourth order scalar ODEs. So again, there might be some very interesting hidden interplay between complex geometry and integrability theory of this integrability of these equations. But it's somehow hidden, so I'm not sure how to. What's the explicit link here? Should be one. So this just again to say that conditions coming from linearizations of equations are usually very rich. By geometric meaning, you might have very interesting interplay with other areas with other domains of differential geometry, complex or real. And we know this very well from integrability, classical Penrose theory, so to say. one more example, and I will probably then move to the discussion. One more example, which I kind of, it's a funny example, but again, it shows what kind of equations one gets by imposing these conditions. That's one of the most general examples I've seen on these equations. So again, it's constructed from writing down explicitly the solution space first. It's just an arbitrary quotient of two polynomials, one of degree k, another of degree L. So this is our solutions, general solution. So a question, how to write the equation of this thing. And so the equation of this thing looks like this. So it's written as a huge determinant. It's kind of a Hankel, Hankel matrix. Yeah, here I assume that k is greater or equal to L. Otherwise, we just change y to 1 by y. And then we just increase the indices by 1 all the time, and I put the expression of the thing. So ZR in general is nothing but normalized. So it's R's derivative of y with some coefficient. So it's here you have k plus L plus v, k plus 2, you get k plus 1, k plus 2, z, k plus L plus 1. So that's about what you get. I've never seen such systems coming from anywhere else, but of course the nature of such system is algebraic, purely algebraic. Because in a way I prescribe a number of zeros and poles of a certain section over rational, over line, over P1.
We need an equation of order L plus L plus 2.
Plus 1, because one of them is so you may still multiply a and b at the same time by the same. So it's k plus L plus 1. This is why you have k plus L plus 1. So it also it has a very algebraic nature, and so far all the equations satisfying the C-class conditions I've seen, they did come from some algebraic reasoning. And I don't know why. So I'm really very interested to try solving such system, even in the simplest case models explicitly, and coming up with some other examples. So I think I will stop here because we are all tired a little bit. It's 5 to 9.
Yeah, it's okay.
Yeah.
Well, if you finish this,
But yeah.
if you want to add something.
No, what is left is ideas behind the proofs, why this thing is of C-class, but it's yet another, like, at least 20 minutes of pretty dense algebraic techniques. So I'd say, and more or less, it doesn't add anything very new comparing to very original Cartan reasoning. So the idea is to understand what kind of connection one can associate with this system, then prove that differential equations, differential invariance of such equation or system of equations is the same as differential invariance of the connection, and then play around with algebraic properties of this connection and understand its curvature. But again, this cannot be done without algebraic guidance, and this algebraic guidance comes from the cohomology theory of real algebras. So that's in a few words the techniques, but if I go into the detail, I would need to explain a lot of additional technicalities, which is probably not, it's already like 1.5 hours of the talk. People are tired, I believe. So instead, maybe some questions or comments or ideas.
You play my role. The audience is silent.
Yeah, probably tired.
Okay, then please give me
Yeah.
my microphone because I have
Yes.
Boris, thank you very much. It is really beautiful.
Mhm.
So I repeat, questions, remarks, comments.
Do you will this painting like this or in this direction for partial differential?
So I mentioned two things here. So one of them is the result of Jennifer Pontov stating that if one starts with a dispersionless second order PDE, just a single one in n variable, one function of n variables. So it's equation written on second derivatives, so to say. And then looks at linearizations along each solution. Now the solution space will be infinite dimensional. So, but you still want, if one has a solution, one gets a notion of a linearization. And this linearization defines now a conformal structure of the solution. So it's different. Here it's just a linear, it was here a linear differential operator. In case of dispersionless systems, you end up with a conformal structure of the equation. So, and of course, invariants of this conformal structure automatically become invariants of the equation. So imposing the conditions that the conformal structure is trivial or trivializable, meaning, well, conformal structure is trivial means it's the same locally as the conformal structure on the sphere. Zhenya was able to prove that then the equation itself is trivializable.
Yes, but I guess that Alec meant is there
C-class equations.
yes,
Yeah.
generalizations of C classes.
Yeah, I was trying to think about this before the call, before this talk, and I came up with the following approach, which might or might not work. So, of course, one needs to go to, so in ODEs, we heavily use the fact that they are finite type. So at a certain moment, it's k+1's prolongation is the same as k's prolongation. So it's not just, yeah, it's all ODEs, yeah. So in case of infinite type equations, so arbitrary PDEs, one has to go to infinite jet. That's it's unavoidable in a way. So one has to look at the action of the pseudo group on infinite jets. And the question is there a chance to find some differential invariance there?
Yes, but the problem is how to define, because you have no first integrals in the case of PDE.
No, instead of first integrals, it might be something
Yes,
yeah.
But what?
Yeah. So this will be still. So for the question, very first question is: does it make sense the notion of differential invariant if you go to the infinite jet? And again, on infinite jets, all solutions will also form, I think, the foliation. No. No. Because like infinite jet will determine formally at least the solution,
well,
like formally.
If you go back from PDEs to ODEs,
yeah,
then the object that transforms to first integrals is a conservation law. So maybe this is a probable direction, but I don't know.
So we have to think about the condition.
How to relate conservation laws with differential invariance is another problem, but maybe. Okay.
So for the moment, there is nothing.
Almost empty. Yeah, almost empty territory, except for some motivation to think about this. C-class, exact reformulation of C-class for PDs doesn't exist yet. But as I mentioned, some ideas where linearization is used to study the original equations, integrability in particular. Integrability theory enlarges Penrose-like integrability, so we speak about this kind of integrability, is enlarged based on studying, to be precise, integrability of hydrodynamic type in terms of Jennefer-Ponte is linked with Penrose integrability of linearizations. Yeah, that's probably because you get conformal structures along solutions, and then Penrose specifies, or Hitchin specifies, what does it mean the conformal structure to be semi-integrable. Like you have a families of alpha plates and beta plates, and some of them have to be integrable. And this condition is equivalent to initial dispersionless equations to be integrable in the sense of hydrodynamic reductions. So, but this is a different line, I'd say. It's not exactly generalizing C-class to PDs. It's just using the principle of linearization. I hope then I put it all correct in words.
Yeah, I'm here. I'm here.
Yeah.
Right.
Yeah.
Okay. So if no one has questions, then I thank you for participating. And the next talk is by Jennefer-Ponte.
Oh, yep.
In a week.
Yep.
Boris, thanks a lot.
Yeah, that's all. Thank you
Sure.
for inviting me here.
Yes, well, you are always welcome. Okay, goodbye.